Fuzzy control of a pH reactor. This will be today's topic in this module 4 on fuzzy control. The last class we learned how a Mamdani type of controller can be designed and also can be optimized using genetic algorithm. Today we will again consider the same Mamdani type of controller, but we will utilize or we will use a different algorithm for optimization, which is differential evolution, as well as the same genetic algorithm. However, the interesting part of today's lecture is that in this the fuzzy logic controller has been implemented on an actual pH reactor fabricated for a laboratory experiment. So, this is the topics, these are the topics to be covered today. pH neutralization process, I will describe what is a pH reactor. Simple genetic algorithm using a smooth search, differential evolution versus simple genetic algorithm, differential evolution based fuzzy logic controller, the experimental setup, simulation and experimental results. pH neutralization process. pH neutralization process contains both nonlinearities and changing process dynamics. What are these things? The nonlinearities are due to the fact that the output of the pH sensor is proportional to the logarithmic of concentration. Although the dynamical equations we will just see they are linear, but linear in terms of the states of this pH reactor. However, the pH, the actual response of this reactor has a relationship with the states in terms of logarithmic. While the changing process dynamics are brought about by introducing a buffer into the system, which significantly alters the response of the system by changing the concentration of the control reagents and by changing the set point. You see that what you are seeing is that, see, normally you see what is pH reactor? pH reactor, many chemical processes, they have their waste product that has to be rejected into the environment. But since these products are highly acidic, before it is rejected to the or it is thrown into the environment, or it is the pH, which you know that pH denotes the normally a pH of 7 means it is a neutral liquid, and more pH means more acidic, less pH means more alkaline. So, this is so we want to keep the pH in a specific zone such that the output or the wastages that are being rejected or that is being released by a chemical plant does not do any injury to the environment. So, it may seem that this is a very fairly simple process, but actually pH control of a reagent or reactant, whatever you say, is is not an easy task because of nonlinearity. You see that nonlinearity is that pH is nonlinearly related to the concentration of the liquid. So, here it is, this is a continuously stirred tank reactor. Okay. This is your input stream, the flow that is coming from the plant, the waste products. This is called buffer. I will explain just now what is buffer. This is the pH sensors, and so this is your controller. The sensor senses the pH of the reactor, and the controller receives that sensor through ADC CAD. And there are, you see that there are two ways you can add control the pH, by either adding acid or adding base, you see, and either you add base or you can add acid. Sometimes also people simply have only one agent to be added, that is either acid or base, but here we have multiple input. You can sometimes select acid, sometimes you can select base. So, 2 input here, and finally, the response output is only single output, that is the response of the pH of the liquid contained in this reactor. So, as I said, changing process dynamics. What is changing? The buffer is something that automatically flows into the system. Okay. So, what is this buffer? Buffer means if once buffer is added to this liquid, even if you are adding externally some acid or base to neutralize the pH content, then because buffer is added, so buffer has the capability, like if it is acidic buffer, it has the ability to absorb the acid more and more, such that even if you are adding more and more base into the system, the pH does not change, or you are adding acid into the system, it does not change, because the buffer has the capability to absorb either acid or the base, depending on whether it is a acidic buffer or alkaline buffer. So, a pH reactor we have fabricated in the laboratory for the laboratory testing. The nonlinearity of the pH dynamics are due to the fact that the output of pH sensor is proportional to the logarithm of the concentration. pH process dynamics changes due to the introduction of buffer into the system, which significantly alters the response of the system. So, that is why it is a variable, because this quantity automatically comes into the through the input stream. Nobody knowingly adds it. It's a quantity that automatically comes. So, the laboratory pH system that we have fabricated consists of following component: a continuous stirred tank reactor CSTR of 20 liter volume, 2 control reagents, acid as well as base. Acid is HCl and base is NaOH, which are manipulated by stepper motor driven needle valves. One input stream whose pH has to be controlled, another stream through which buffer acetic acid can be introduced. The physical system, the metering range of control valves are 0 to 0.02 liter per second with an increment of 0.0002 liter per second. So, this we have fabricated the valve in such a way the input can be varied at any time between 0 to 0.02, and the incremental change in this input can be with the resolution of 0.0002 liter per second. So, this is the final resolution we have. The objective of the control problem is to drive the pH of the system to the desired set point in the shortest time possible by adjusting the valves of the control reagents 3 industrial pH electrodes were used to account for the spatial non-uniformity with the reactor. What we have done here is that you see here I have put only one sensors schematically shown, but in actual experiment these sensors we have put in 3 places, 3 different places in the CSTR, such that any kind of spatial non-uniformity can be taken into account by averaging the sensor output of these 3 sensors placed in 3 different locations in this CSTR. The pH sensor signals were transmitted through a 12-bit add-on ADC card Dynalog microsystems PCL207 to a 33 megahertz 386 IBM PC, which controlled the entire process. A sampling time of 30 millisecond was used throughout the study. So, here some of the parameters that we have utilized we have used for describing the dynamics of the pH reactor. This is, you see that obviously you can easily see the concentration, C stands for concentration, this is the inlet. So, inlet buffer concentration, okay, because you saw that to our tank, if this is my CSTR, so we have 2 input, one is buffer, another is actual input stream, whose pH has to be computed of this, when this is the input stream, and we have to control the pH of this input stream before this this liquid goes to the environment or is released to the environment. So, the buffer the concentration is C in, Ca in is inlet acid concentration, Cb in is inlet base concentration. So, here in the input stream, what is the concentration level of the acid and concentration level of the base. This is chloride ion concentration Cl minus, Fa is acid flow rate, A stands for acid, F stands for flow rate. So, acid flow rate in liter per second, Fb is base flow rate liter per second, Fe in inlet flow rate, this is the acid flow rate, base flow rate, these are all control variables. These are control variables. Fin is input flow rate, we have no control over it, the input coming from the plant. F out is the output flow rate, and this is the H plus is the hydrogen ion concentration. These are 2 different parameter K and Kw, they represent equilibrium constant for this CS3COOH, and this is equilibrium constant for H2O. Na plus is the concentration of the sodium ion, and V is the volume of the CSTR. So, this CSTR has specific volume, that is V. So, given that, you can follow any standard book to see how the dynamics so of the this is the concentration zeta, which is the concentration of HAC and AC minus, and so V is the volume. So, V d zeta by dt is F in the input flow rate in input concentration minus F out into zeta. Similarly, volume into sodium ion concentration rate, the rate of change in sodium ion concentration is base flow rate into base concentration, input base concentration in the input stream, minus F out, output flow rate, into sodium ion concentration, and here V chloride ion concentration, change in rate of change in chloride ion concentration is Fa, the acid flow rate into the acid concentration in the input stream, minus F out is the output flow rate into chloride ion concentration. So, you see that finally, the solution of this, we solve for the hydrogen plus concentration, hydrogen ion concentration, and pH is defined as minus log of 10 hydrogen ion concentration. So, hydrogen ion concentration is related, you see, hydrogen ion concentration cube plus Ka plus xi into hydrogen ion concentration to the power square into K xi minus zeta minus Kw into hydrogen ion concentration minus Kw into K equal to 0. So, if I solve this, so you see that this equation is dependent on zeta, which is the solution of this equation. This is zeta and this is xi, sorry, zeta and xi, and so you get zeta from here, and you know that Na plus you get from here, Cl minus. So, if I update this equation this continuously, I get 3 variables, 3 states, zeta, sodium ion concentration, chloride ion concentration. Sodium ion concentration minus chloride ion concentration gives me xi, and zeta gives me the solution zeta. So, this equation is a function of zeta and xi, the states of this equation. So, I solve this equation, and then I put this zeta and xi in this equation, and so and Ka is a external coefficient, Kw is another external coefficient. By putting this, I solve for H, which is a nonlinear equation, and then pH is minus logarithmic of H plus to the base 10. So, what we discussed until now is that how the dynamics of a pH reactor is actually nonlinear, and also we described that a pH reactor, and this is nonlinear because the concentration and pH are nonlinearly related. Now, so we will be designing a physiology controller. So, we have to optimize the parameters, as we said in the last class. We introduced in the last class 2 algorithm, one is SGA, simple genetic algorithm, another I hope you have remembered what is UMDA, univariate marginal distribution algorithm. So, there I showed you that how univariate marginal distribution algorithm does very well compared to simple genetic algorithm. So, that is why we will be talking about a smooth search today that can help to improve this simple genetic algorithm. Simple GAs are prone to premature convergence when used to optimize multimodal convergence, as a string which represents a local minimum might duplicate. So, that is, if my the error surface, this is my error surface, this is my parameter p, and this is my error cost function or error function. So, for example, I am here, and most of my strings are duplicated in this zone somehow, whereas my actual minimum is here or here. So, then we are trapped in a local minimum. So, simple GS suffer from the fact that convergence is too slow to apply to optimize a controller for real time control. In real time we have to optimize it very fast. This drawback can be eliminated to some extent by using source space smoothing technique. For source space smoothing technique you can follow this paper that appeared in IEEE Systems Men Cybernetic in 1994. In smooth search, a smoothing factor alpha is used to characterize the degree of smoothing operation and the smoothness of the resulting search space. If alpha equal to 1, no smoothing is done and search space is same as the original search space. If alpha is greater than 1, a smoothing operation is applied and smoothing search space is flatter than the original search space. If alpha is much greater than 1, the smoothing effect is very strong, gives rise to nearly flat search space. So, pictorially you can easily see this is my actual, this is my the actual space, search space in which I am moving. Okay. That is what you are seeing is that this is my the error curve or cost function versus the parameter curve, the parameter for which I am trying to minimize or optimize the cost function. So, what is meaning of the smooth search space is that I am introducing a new parameter called alpha. So, when alpha equal to 1, I get back or I recover my original smooth space as search space, but when alpha is greater than 1, you see that the search space becoming flattening, and when alpha is very large, you see this almost flattened, which has only one minimum. You see that this has only one minimum. So, what is the objective? Objective is that what we do in this search space smooth search space technique, we increase the alpha to a very high value in the beginning, such that my search is in the flat surface where I have only one local minimum, and then I decrease the alpha slowly so that finally I recover my original search space, but my solution space will lie only in this zone. Okay. So, this is the understanding of a search space. The fitness function in a genetic algorithm is expressed for the control. This is for controller control. So, what you are seeing epsilon square is my error, tracking error. Okay. This is my tracking error from 0 second to 30 second, and case 1 to case 4 means this is from different initial condition. Okay. So, I can always control my pH from various initial condition. Okay. So, but from any initial condition I start, finally from all initial condition I should reach the actual pH with a minimal cost function. That means, my tracking error should be minimal, that is the cost function should be minimal. Okay. So, the initial condition cases were selected from different regions of the state space of pH control system. So, what you are seeing is a series of smooth search space is generated. The smoother search space are used to guide the search of those of the original search spaces. So, since in the original we have more local minimum as well as a global minimum, and I may be trapped here or here, through smooth search through the smooth search I am avoiding these things and reaching here, right. The smoothing function applied to the genetic algorithm is expressed mathematically. This is my cost function, this is my average cost function, okay, average cost function of my this is the individual cost function, and this is my average cost function, So, my individual cost function can be written in terms of the average cost function plus the individual cost function minus the average cost function to the power alpha. You see in genetic algorithm we have many the population consists of many solution space. For each solution space we have a specific value of fitness function, okay. And the fitness function is given by this. This is my actual f. So, I am representing this fitness function in terms of an alpha. I am introducing a parameter alpha, because if you see the previous one, this is not, this is independent, this is not a function of alpha. So, I am introducing an external parameter alpha, here I am introducing an external parameter alpha in such a way, you see that this is my you see that there is an average fitness is individual fitness of all the solution space, and then I average it. So, that is called average fitness, and this is my actual individual fitness minus average fitness to the power alpha. So, if I put alpha equal to 1, you can easily see f I is simply f I, okay. And here also similarly alpha equal to 1, if I put here, so then f cancels out and minus is plus f I. So, f I alpha is f I, okay. And whereas when I have alpha is very large, very large, okay. So, I can easily say that this quantity because this is normalized values f I and f bar, these are all normalized. So, f I minus f bar is a fractional quantity. So, when alpha is very large, obviously this term vanishes. So, f I alpha becomes f bar, okay. So, it is a flat surface. So, where f I is the fitness of the ith individual, f bar is the average fitness, and alpha greater than equal to 1. Alpha is decreased gradually from a large number from 10 to 1. A search space generated by a larger alpha exhibits a smoother terrain surface, and that generated by smaller alpha exhibits a more rugged terrain surface. Those two extreme cases of functions are, if alpha is much greater than 1, then f I alpha is f bar, this is the trivial case, and if alpha is greater than 1, then f I alpha is f I, which is the original problem. Okay. So, this is what we wanted actually. So, we take a very large value in our experiment, we have taken alpha in the beginning around 9 and we have reduced until alpha equal to 1. So, that is what we talked about, that this concept of smooth search space idea can be augmented with genetic algorithm to make the genetic algorithm very fast. So, that is simple genetic algorithm augmented with search space, smooth search space. Now, here I will present, earlier we have discussed about simple genetic algorithm, univariate marginal distribution algorithm. Today, I am introducing you again another new kind of optimization algorithm, which is also called evolutionary computation algorithm, which is here it is differential evolution. The differential evolution algorithm is developed by Price and Stone in 1997. The idea is that we have an initial population as usual earlier. It consists of NP parameter vectors of dimension d. So, obviously, I am optimizing d parameter vectors and my population size is NP. So, you see that each parameter vector is represented by xi gamma, where I equal to 0 to NP minus 1. Okay. This is my parameter vector and its dimension is d. So, unlike in genetic algorithm, what we do, given initial population, we make a selection and according to fitness, and then we and mutation. But here this variation, a new population is generated using trial vectors. You see, this is trial vectors. What is a trial vector? For each parameter vector in the initial population xi gamma, a trial vector v is generated for each xi gamma. And what is this v vector? The trial vector is the original parameter vector plus lambda. This is the best parameter vector, means the parameter vector having optimized fitness and our highest fitness, minus the present the original parameter vector for which we are creating a trial vector, or we can say this is a target vector, target parameter vector for which we are creating the trial vector, plus f into x r 1 some arbitrarily randomly selected another parameter vector from the population, and r 2 represents another parameter vector from the population. So, r 1 and r 2 they represent two randomly selected parameter vector from the population. Okay. So, it is like this. If this is my zone, in this zone in this space, if this is my r 1 vector, this is my r 2 vector. So, what I am trying to do is that, so this is my say reference point, this is at r 1. So, I am subtracting this vector as a r 2 vector from r 1 and multiplying this with a constant, real constant f, and then I am adding this difference with the original target vector to create a trial vector. And this is this second term that is being added. The main objective of trial vector is that I select two random vectors, two random parameter vectors from the actual initial population, from the population, and then magnify or I multiply that difference with a real constant f and add that to the actual target vector to create a trial vector. The second term is simply is the idea behind lambda is to provide a means to enhance the greediness of the scheme by incorporating the current best value, which is x best, the parameter vector that has the maximum fitness. So, this is just an additional thing, but usually the parameter vector is the target vector plus difference between two random vectors, randomly selected parameter vectors from the population and multiplied by a real constant. So, the integer r 1 and r 2 are chosen randomly from the interval 0 to n p minus 1 and are different from the running index I. It cannot be the same index as I. F is a real and a constant factor that controls the amplification of the differential variation. The idea behind lambda is to provide a means to enhance the greediness of the scheme by incorporating the current best value. The current best value is represented by the parameter vector in this population. So, once I create a trial vector, you see that if my population size is n p, then my trial vector size also is n p. Then what I do? I do a crossover. Okay. Once I create this trial vector, I perform crossover on this trial vector in this manner. What I do is that I create define two parameters n and m, and they are random integers. N and m, they are random integers. N can be any integer, but the integer m is drawn from the interval from 0 to d minus 1, because each parameter vector in the solution space consists of d parameters, because our the actual we are considering a parametric space of size d. Okay. So, with the probability, so integer m is drawn from this with the probability m is some value, this is you see the small gamma which lies between 0 to d minus 1, which is CR. This is crossover probability. CR is known as crossover probability to the power gamma. So, normally CR is less than 1. Okay. So, if you take 0.9 okay, to the power gamma. Okay. So, higher value of m means less probability. Okay. So, CR is the crossover probability. So, what I am trying to do is that given the trial vector, a new parameter vector u is obtained, where my the crossover output of u1, u2 until ud, because I have d parameter vector, the parameter vector consists of d elements, and the jth element is Vj, means I retain the trial vector element if j equal to n modulus d, n plus 1 modulus d until n plus m minus 1 modulus d. So, what is this modulus? You remember that this is the quantity, I divide d, whatever the modulus means the modular function means the remainder is 0. Sorry, this close bracket d implies the modular function. Okay. So, if j equal to modulo d means the remainder, if I divide n by d, I must get j. Okay. So, if that happens, then I retain Vj. Otherwise, I take the element from my target vector, the jth element of the target vector. So, what we are trying to do is this: for x I gamma, I created a trial vector v, then I am doing a crossover between this target vector and the trial vector to find the actual new population vector, new parameter vector in the population. So, what I do is that for that I select two parameter n and m in such a way that I retain the elements of v as long as the modulo functions, any of these modulo function is equal to j. Otherwise, I take the element from x into this. Okay. So, you see that the bigger is m, less likely I will select, and so this is the objective. Objective is that it is a very probabilistic way of mixing the elements of v, the target trial vector and the target vector in such a way to create a new solution vector. So, new solution vector is obtained by the crossover between the original target vector and the trial vector. So, once the crossover is over, the selection is compare the fitness of the new parameter vector, which is u bar. So, what we found out that u bar, the crossover is my target vector, and I can put an I for indicating target vector, crossover CR V. I am getting a new parameter vector. So, the vector with the optimal cost is rewarded by being selected to the next generation. So, unlike the selection that we did for genetic algorithm or for univariate marginal distribution, we saw that here the selection is not the comparison among all the parameter vectors, but comparison between the target vector, parameter vector from the population and corresponding the new vector generated u from the target making the crossover between the target vector and corresponding trial vector. So, now we have to find out the fitness of x I and the new parameter vector u So, if u fitness is better than the target vector, then u becomes the new parameter vector in the new becomes the parameter vector in the new population. Okay. So, among these two, one of them will be selected to the new population based on the fitness. So, only two of only target vector and the corresponding new parameter vector, their fitness is compared. So, repeat the process NP times, which makes the generation complete. See, if I find like that NP new parameter vectors, then I get a new population. And again I start from the beginning for each trial vector parameter vector in the new population, again I find a new trial vector. So, now we will have little discussion on the simple genetic algorithm and the differential evolution. I wish that you are clear about what is differential evolution. A simple genetic algorithm uses binary strings to code the parameter vectors. Imagine we talked about that, and however, this choice limits the resolution with which an optimum can be located to the precision set by the number of bits in the integer. However, in contrast, differential evolution uses floating point numbers, which not only uses computer resources efficiently, but also reduces the computational time, which is very crucial for control application. While use of search space smoothing aids faster convergence of an simple genetic algorithm, it still takes substantially more time to converge as compared to differential evolution. Here we can see that this is differential evolution, very fast convergence, whereas this one is simple genetic algorithm, this dotted line, and this is pretty slow convergence. The convergence of differential evolution is much faster than simple genetic algorithm. As clearly depicted, the differential evolution converges almost in 3 generations in this particular example, and also to a much lower value. Okay. Whereas, simple genetic algorithm takes almost to 20 generations or so. So, given that, now we will be talking about the FLC controller architecture. So, this is my physiology controller, this is my plant pH reactor, this is the disturbance is actually buffer, output of the plant is the pH, and this is my the set point pH. Normally the pH is set is as 7, and here the error and the derivative of the error, these are the 2 input variable to my physiology controller, and I utilize differential evolution to optimize the parameter of physiology controller. The output of physiology controller is either acid flow rate or base flow rate to the plant. So, DE-FLC design, the input parameter for FLC, the error and derivative of the error had their base lengths determined by the differential evolution, while the location of the peaks were kept constant. What is meaning of that? If this is my epsilon, okay. So, what I do, given any fuzzy membership function, I fix the peak for that linguistic variable, where the base, what is the distance between this point to this point. This is optimized using, what is the base length is optimized using the differential evolution. The rules used were of the form, if error is either negative high, negative medium, negative small, negative 0, 0, positive 0, positive small, positive medium, positive high, and the derivative of the error is negative medium, negative small, 0, positive small, positive medium, then output, where output is the acid or base flow rate. So, you see that the rule base size has to be 1, 2, 3, 4, 5, 6, 7, 8, 9 into 1, 2, 3, 4, 5. So, 45 rules. So, we have in our this particular fuzzy logic controller 45 rules, and we have assumed that our output is simply singleton for the So, you see the outputs were singletons to ease the computational burden, no additional parameters were required for them. Okay. So, and for each fuzzy partition, because I have two variable, and for fuzzy partition of each variable I need only, say for example, my error is fuzzy partition into 9 fuzzy linguistic variable, and for differential evolution has to find only 9 parameter corresponding to that, that is the base length. Okay. So, this length is determined by the differential evolution. So, total number of parameters that I need is 45 parameters for the output and 9 parameters, 9 base lengths for the fuzzy variable error, and 5 base lengths for the fuzzy input variable, the derivative, the change in the red derivative of the error. So, the total is 9 plus 5 into 45 is 59 parameters that we have to optimize. The outputs were singleton, that I have already told. The first 45 vectors of each parameter vector from the rule set form the rule set, and the next 9 vectors from the base length of error membership function, the rest the base length of the derivative of the error membership function. So, that is how we get 59. The rule set consisted of flow rates of the control reagents, which were classified as, so that is the output is classified as very large acid flow rate, large acid flow rate, medium acid flow rate, small acid flow rate, 0 flow rate, small base flow rate, medium base flow rate, and large base flow rate or very large base flow rate. So, this is how the output is fuzzified. The minimum overlap between two adjacent membership function was chosen to be 0.2 and the maximum to be 0.8 to ensure that at least two membership functions exist throughout the state space. So, doing this, when we did the optimization, you see that I have a variable base length. The base length were decided by differential evolution. My error fuzzy partitioned into 9 linguistic variable 1, 2, 3, 4, 5, 6, 7, 8, 9. The peaks are fixed, only the base, you see that this is the base that is obtained by the from the differential evolution, like for this particular one. So, from here this is the base length that is obtained, and this particular value was actually the peak. Where is the peak? That was fixed a priori. Similarly, the derivative of the error also the base lengths were obtained in this particular manner. The final membership function at which the differential evolution converged. Now, simulation response, we first did the simulation for the theoretical model that we obtained. So, here what you are seeing, the flow rates, the buffer, acid, base and base, that is how the input stream, and here is our. So, you see that what we are trying to do is that the pH is controlled at its neutral value 7. So, you can see this is the value is 7, and you see that in the beginning the actual input stream has a pH of 4 and that goes to increase 7, and you see that because acid is added here, there is some dip. So, the mistake, the figure should have been little expanded, this is not to the scale, and then so actually this dip is due to this particular effect, and this effect is due to the base, and again this sudden hike is due to the base. Okay. Simulation of the response of DE-FLC for perturbances like addition of buffer, acid, base. So, in the beginning when I add a buffer, it takes long time to jump to the actual pH 7, and then acid pH goes down, base pH goes up, and addition of base, this is the disturbance added, but always finally the pH is maintained at 7. So, this is our experimental setup. You see that we controlled using a PC. This is our reactor, okay, which is fabricated in the lab, and the entire controller was implemented using PC. The experimental strategies: the performance of the adaptive differential evolution physiology controller is demonstrated for three different situations. First, the pH system is perturbed with the external addition of an acid, a base and a buffer, along with a continuous input stream of pH 8. In this case, the process dynamics are dramatically altered by the addition of a buffer. Second, the desired set point is altered, which for all intents and purposes changes the objective of the controller. Third, the concentration of the control reagents are changed, which causes the system to handle differently. Strategy 1, the pH system is perturbed with the buffer, acid and base. DE-FLC parameter are taken after 3 iterations, and the performance is compared with a GA-FLC parameter, GA-FLC based controller, whose parameters are taken after 100 iterations. So, usually you see that while optimizing, I am only going for 100 generation, I am going only for 3 generations for DE-FLC, while 100 generation for GA-FLC. The performance of DE-FLC is compared with that of GA-FLC. The results show that DE-FLC is much more efficient in terms of faster settling, lesser overshoot and steady state error. So, you see here that here the acid is added, here buffer, here base, and here again base. So, you see that genetic algorithm is the dotted one is the genetic algorithm, whereas differential evolution is the solid line. So, you see the genetic algorithm has based controller has more overshoot here, and here also more overshoot, here is more undershoot, here is more undershoot, and also there is some error, steady state error in case of GA, whereas in case of differential evolution we get constant pH. This is experimental result. This is experimental result. So, perturbation by addition of buffer, acid, base, DE-FLC shows better performance than SG-FLC. Now, strategy 2, consider a situation where the set point is changed, which implies that objective of the controller is being changed. DE-FLC parameters are taken after 3 iterations, while GA-FLC parameters are taken after 100 iteration. The performance of DE-FLC is compared with that of GA-FLC. The DE-FLC outperforms GA-FLC. You can see here. Now, set point earlier here was 9, then it was changed to 6, to 8, and then 5. So, you see that the comparison between GA and DE, D is the straight line, a solid line, and GA is the dotted line in the GA is the experimental result. Okay. So, in this case, in this zone, GA is a little better than D, but you have to see that GA parameters were optimized using 100 iteration, 100 generation, where D is only 3, and here if you look at in 6, D differential evolution is much better than the GA, and when it is 8 also the GA D better than GA, and whereas when it is 5 again D is better than GA. So, here DE-FLC performs efficiently compared to SG-FLC. Strategy 3, consider the case wherein the concentration of the control reagents are changed. This is the most disruptive perturbance, since it changes the system response completely. The DE-FLC parameters are taken after 3 iterations, while GE-FLC parameters are taken after 100 iterations. DE-FLC is able to maintain a high degree of control over the process despite the drastic change in the environment, which is clearly depicted. FLC augmented with DE is able to maintain a high degree of control over a bench scale pH setup despite the nonlinearity and dramatic perturbations. So, you see here how the response is. Okay. So, from 9 to 6, again from 6 to 8. So, you see that DE maintains. So, change of concentration of control reagents from 0.5 N to 0.1 N, DE-FLC has less effect of parameter changes as compared to SGA FLC. So, SGA certainly gives some steady state error, here also some steady state error. So, these are all experimental results. In summary, we would say differential evolution is used in the simultaneous design of membership function and rule sets for fuzzy logic controller. In the last class we showed optimization using simple genetic algorithm and univariate marginal distribution algorithm. Differential evolution is an exceptionally simple, fast and robust population based search algorithm that is able to locate near optimal solution to difficult problems. This technique, which is similar to genetic algorithm, has been applied to the control of pH, which is a requirement in many chemical industry, and not only we did it for simulation, also for experiment. Control of pH poses a difficult problem because of inherent nonlinearity and frequently changing process dynamics. The DE-FLC has been successfully implemented on a laboratory scale pH plant setup. The results have been compared with simple GA based adaptive FLC, where we have incorporated a source based smoothing function for achieving faster convergence and for ascertaining a global optimum. You see that today the DE is compared with the SGA, but SGA has been augmented with smooth source space. Still DE is better than SGA. Results indicate that FLCs augmented with the DE offer a powerful alternative to GA based FLCs. Results also show that the source space smoothing function halts in faster convergence of a GA. So that is in this lecture series on intelligent control. We will stick to these 2 lectures on Mamdani type of fuzzy logic controller and their optimization. Next lecture onwards, we will be concentrating on TS fuzzy model. Before we go to TS fuzzy model, I will give a little transition, and then transition, that is the next lecture. In the 4th lecture, I would show you that how intelligently we can actually generate the rule base for fuzzy Mamdani type of controller, such that the control system as a whole is stable, which is very interesting. Thank you very much.